Osseous tissue is made up of several different types of cells. Now, these osteogenic cells, we're going to start the discussion with the stem cell, this osteogenic stem cell. Basically, the osteogenic stem cell is going to give rise to the other osseous tissue cells. It's what creates the cells that make the actual matrix, that create this calcified matrix. These osteogenic cells originally are coming from the fibroblast cells. So fibroblast, remember that's the generic cell that starts all connective tissue. So if you're not sure about what fibroblasts are, head back to the histology lectures. But the osteogenic stem cell arises from the fibroblasts of the basic embryonic tissue. Now, this osteogenic stem cell can give rise to future cells in the osseous tissue. It can give rise to the osteoblast cells, for example. Osteoblast cells, these are the ones that are creating or making the bony matrix, making the actual calcified matrix of the osseous tissue. So when you start looking at these osteoblast cells, you'll notice this box right here, that's right in the outside edge of the bone. That's where the periosteum is. That's where you create the new bony matrix. It could also be found in the endosteum, so inside the bone too. But the idea is it's always on the outside edges of the bone, so it can lay down new calcified matrix and create more bone itself. So this is how you form the bone. Remember the term blast. Blast is forming or making a tissue. So in this case, the osteoblast is making the osseous matrix. But now, when an osteoblast cell becomes trapped inside of the actual calcified matrix, it becomes an osteocyte. The osteocyte cells, remember CYTE, cyte, is meant to maintain their mature cells. You'll notice that these osteocytes, they have them coming from the inside of the actual bone matrix, inside that calcified osseous tissue. It's in there that's monitoring stress and strain on the bone, seeing if there's adequate calcified matrix to accomplish what needs to be done, or if there's too much stress and strain, we need to add more calcified matrix to make sure the bone is strong enough. So these osteocytes, they're monitoring the bone, keeping it healthy, detecting strain on the bone. But there's one more yet, the osteoclast cells. These osteoclast cells are a little bit different now because while the osteoblast created the bony matrix, the osteocyte maintained the matrix, the osteoclasts are meant to destroy the matrix. These osteoclast cells will help to dissolve the calcified matrix of the osseous tissue. The reason you'd want to dissolve the matrix, break down the actual bone, is because that way you can release calcium into the blood. Remember, calcium is a storage in the bone, so the bone's kind of a reservoir for calcium. But also, it helps to remodel the bones. As you're growing throughout childhood, the bones are growing in length and width, they're growing up a ton. You gotta make sure they maintain the proper shape. This osteoclast cell can help to remodel to maintain the shape. So osteoclast, these are bone dissolving. So dissolving the bony matrix, dissolving that calcified matrix of the osseous tissue. So really, what is in this matrix I keep talking about? I keep talking about making the matrix, destroying the matrix. Well, the matrix is made up of organic and inorganic components. Now, the organic can see things as the bone cells and as the osteoid. The osteoid, we'll learn later, is going to help with causing the mineralization of the bone. But this is all non-mineralized components. Give or take about a third. I have down here 35%, but I think it depends on each individual person. So about a third of that matrix is going to be organic material. Things like protein, collagen, you have your ground substance, water. It's the non-crystallized, the non-mineralized components. While the inorganic is the mineralized components. You see this term hydroxyapatite. The term hydroxyapatite is the structural kind of crystalline structure that's found inside of the actual matrix. It's where a lot of the calcium is put into and how it creates the shape and structure that gives the strength to the actual system. Now, it's not the only thing giving strength, because crystal by itself can be very fragile. It's a combination of the collagen, the organic, and the inorganic crystalline structure. But the inorganic here is about 65%, so about 2/3, give or take. That means majority of your osseous tissue is inorganic material. Looking at things like calcium phosphate, calcium hydroxide, and calcium carbonate. Different calcium-based structures that give the structure and the strength into the actual matrix. Now, all this matrix, all these cells, when they come together, they're building structural units. So if we look at the compact bone to start with. Now, the compact bone, we're going to start with what's called the osteon. Hopefully that rings a bell back from the histology chapter. The osteon was this circular unit. So the whole circle with all the rings is the actual osteon. You then have the central canal. Central canal is going to be this structure, kind of circling it in. That's the very center of the osteon. The central canal is where your blood vessels, so like artery and vein, as well as your nerves are found. So the central canal is a hollow structure that allows your arteries, veins, and nerves to run through. The term lamella. Lamella, you can see here I have the matrix concentrically arranged around central canal. Basically, that means it's the ring structure. So each individual ring, we're going to have one ring around the outside here. Then we have a second ring. We have a third ring. So each individual ring is going to be an actual lamella. So each individual ring. Now, the osteocytes, so the cells, they're trapped in between each ring. So in between each lamella. But they're trapped inside of a structure. They'll be trapped inside what's called lacunae. Lacunae is going to be this structure. So you have the actual cell inside and the structure around it. This is creating kind of a compartment for where the actual osteocyte is found within. So that is lacunae with the osteocyte inside. But each one of these lacunae, so each one of these structures, is connected by tiny hair-like fractures called caniculi. These caniculi are little tiny lines radiating out and around. The idea is these tiny little lines, these tiny little fractures, are going to allow for the actual diffusion of nutrients, waste, gases. It's how the cells stay alive. And then we have these things called perforating canals. A perforating canal, you can see one right here, and a second one right there. But the perforating canals, they're connecting the central canals because each central canal runs down through the canicules, right down through the actual ostia. But you have to somehow connect the blood vessels together to make sure they all have blood supply. So the perforating canals connect blood vessel to blood vessel or chamber to chamber for central canal. But now the spongy bone is different. While the compact bone had the osteon, the spongy bone, also known as cancellous bone, is going to have these kind of like branches things. They're called trabeculae. The trabeculae are what make up the structure inside of the actual spongy bone. So there's a little different structure here. There aren't any osteons. It's all trabeculae. The trabeculae create that kind of framework, that structure. And these trabeculae help to dissipate the forces applied to the bone. It dissipates it throughout the entire area to make sure not one single area has too much stress or too much strain on it. So the trabeculae are in spongy bone, while the osteon is in the compact bone. And in between these tuberculi, a lot of times they're filled with bone marrow. Now again, that depends if it's going to be found in the axial skeleton, if it's out in the appendicular, but either way they have bone marrow. It just depends on if is it mostly red bone marrow or is there yellow bone marrow as well. So some structural components of the actual compact bone and the spongy bone and how they're built.